Hello all the students. In today's video we are going to study distributive lattice. So what is a distributive lattice? A lattice L is said to be a distributive lattice if for all A, B, C that belong to the lattice these two conditions are satisfied. Now obviously A, B, C here represents the element of the lattice and L is the lattice itself. Now we will consider the following Hash diagram. So this is the Hash diagram that we are provided with and it is a lattice. So our task is to find out if the given lattice is distributive or not. So let's see. Now for a lattice to be distributive, the following properties must be satisfied as we have just studied. For any three possible combination of elements from the lattice, these two conditions on those elements must be satisfied. Now here I am saying any three possible combinations. Now a lattice may have many elements, but at any given point of time, out of those elements we can choose only three elements and then we will consider those three elements only in these two conditions, right? This means that we have to consider three elements at a time. Those three elements could be any three random elements from the lattice and obviously they must be elements of this particular lattice only. So let's find out whether this particular lattice is distributive lattice or not. Now before I proceed further, let me tell you once again that A, B, C represent any three random elements of the lattice, and for all the elements of the lattice we have to make these possible combinations. For all the possible combinations of the lattice of all the elements of the lattice, these two conditions must be satisfied, but only three elements at a time. Now let's consider the elements B, C and D. So I have chosen three random elements out of 5 elements of this lattice. So at this particular point of time I have taken these three elements B, C and D. That means instead of A I have B here. That means this particular A represents B, this particular B represents C and this particular C represents D. So my A, B, C here are B, C and D. Now first of all, for the first condition I will choose the LHS. That means obviously first of all I will see if my first condition is being satisfied or not, and for this first of all I will take the LHS. So what is the LHS? LHS says B or C and D. So what is C and D? C and D means the greatest lower bound of C comma D. So what is the greatest lower bound of C comma D? If I trace downwards, C and D meet at A, or the first meeting point of C and D is A. So clearly the greatest lower bound of C comma D is A. So that means I can write B or A. Now what does B or A mean? B or A means the lowest upper bound of B comma A. So what is the lowest upper bound of B comma A? Obviously they both first meet at B. If I trace upwards I can clearly see both B and A are first meeting at this particular point. So the least upper bound of B comma A is B. So that means LHS is equal to B. Now for the RHS I will see that what is RHS? RHS is equal to B or C and B or D. So first of all I will process this particular parenthesis, that is B or C. What does B or C mean? B or C means the least upper bound of B comma C. What is the least upper bound of B comma C? If I trace upwards, E is the first meeting point of B and C. That means the least upper bound of B comma C is E. So that means instead of this B or C I can write E over here. Similarly, what is the least upper bound of B comma D? Again the first meeting point of B and D, if I trace upwards, is E here. So that means the least upper bound of B comma D is also E. which gives you E and E. And what does this and mean? This means the greatest lower bound. So that means I am talking of the greatest lower bound of E comma E. So what is the greatest lower bound of E comma E? It's quite obvious that it is E itself. So RHS is equal to E. Now my LHS is equal to B and my RHS is equal to E. So it is clearly visible that the LHS is not equal to RHS. So I will not proceed further because the first condition itself is not satisfied. So there is no point moving to the second condition. And also, since for the first three random elements these two conditions are not satisfied, that means we do not need to see any other possible combinations of other three elements, right? So if for the first three elements itself these two conditions or any one of the two conditions are not satisfied, we need not consider any other possible combinations of other three elements, right? So we can clearly see here that this particular lattice is not a distributive lattice. So this is all for today's video. I hope you understood. Thank you for watching.